And so, how do we reconcile the two? How do we put the two together? So, I'm going to show you in very simple geometry that the two agree with each other. That actually the two are complementary, that you can't have infinities without finite boundaries, and you can't have finite boundaries without infinities. We'll start with a circle, and we'll say that this circle defines a space, a finite space. And remember here, that circle could be a sphere, right? It could be a sphere that defines a space. And inside it, I'm going to put an equilateral triangle. Now, that triangle in a sphere could be a tetrahedron, right? So, a tetrahedron is the fundamental geometry, Platonic geometry, three faces with a triangle base. And we could say that the universe has spin, right? Everything we see seems to have spin and is polarized. So if it's polarized, then there should be a reverse triangle. Now, you know, interestingly, for the people that are interested in that section of the lecture, right away we have a symbol that's found in many, many different ancient cultures all around the world. Now, notice when I polarized the triangle, what happened? Right away, I defined a new set of boundary that's exactly the same geometry I started with, but at the next scale, at the next iteration. I can polarize that, and now I've done it again in the next scale over. It's very important that you understand that each of these boundaries define a very specific coordinates in space-time. That is, that the center of each of these boundaries is actually on its own very specific coordinates. Although it's part of the whole system, each one is a complete individual because it observes from its own very specific perspective in which no other boundary can observe from. You all following this? So, I polarize that. And now I get even smaller boundaries. And I could continue to do this and get smaller and smaller and smaller and smaller and smaller and smaller boundaries. In fact, if I give this geometry, if I give this program to my computer and I ask it to keep doing boundaries and then zoom in and then keep doing boundaries and zoom in and do boundaries and zoom in, it would continue to make boundaries to infinity and beyond. However, I would never, ever, 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 ever exceed that first boundary that I started with. I would never come out of it. I would continue to divide within the context of what appears to be a finite space. Now, remember, each boundary defines a very specific set of coordinates from which it observes the universe from, right? So each boundary represents a very specific set of information. Each boundary thus represents a very specific set of energy. And so, if I can divide to infinity within the context of a finite space, that means I could have infinite amount of information inside the boundary of a finite space. Infinite amount of information. Why is this important? It's important in many different ways. It's important in philosophy, it's important in spirituality, it's important in physics. Why is it important in physics? Because if the mainstream scientific community understood this, we would stop building accelerators. Right? Not so long ago, the scientific community got their first microscope, and they saw the cells at the biological level, and they said, oh my God, cells are so small. They must be the smallest thing the universe does. And then we had atoms. We realized that cells are made out of billions of atoms, and we went, oh my God, atoms are so teeny. They must be the smallest thing the universe does. And then we discovered that in the middle of atoms, there's a teeny weeny little beady little dot. Protons and neutrons, and we said, oh my God, those are so teeny. They must be the smallest thing the universe does. And then we start to scatter, with building accelerators, colliding atoms and getting smaller chunks